On a hot day, rails heat up in the sun and want to expand, but they're held in place by the track. So the force builds, and if that force isn't understood, that's how a piece of track that looks perfectly fine can still buckle. In this video, I'll show you how rail stress is managed and how engineers check it in the real world using verse testing. Let's start with the terms, because when people say rail stress, they're often referring to the state the rail is in and its stress-free temperature. When referring to stress, track engineers are normally referring to the process of installing the rail in the track in a state of tension. The rail is installed with a gap left at the end, and then special equipment is used to pull or stretch the rail prior to it being welded. This rail is now in a tensile stress state. It's being held in tension because it's welded into a continuous length, so it can't freely change length. And that restraint is then transferred into the track through the fastening system, the clips and pads, into the sleepers, and then the track bed. Why is this done? It's to manage what happens as the rail temperature changes. When metal warms up, it tries to expand, and when it cools down, it tries to contract. Because the rail is held in place, those temperature changes show up as tension or compression in the rail, rather than the rail being free to move and change length. As the rail warms up, the tension reduces because that warming is cancelling out some of the tension it was put in during stressing. That is, until you reach the stress-free temperature, or SFT. The SFT is the temperature where the rail is neither in tension nor in compression. Compression? Yes. Once the rail temperature rises above the SFT, the rail moves into compression because it's being restrained from expanding further freely. And as that compression builds, the risk of a buckle increases because the track is trying to find a way to release that force. SFT is the key number. The higher it is, the hotter the rail can get before it moves into compression. Now in the UK, the target SFT is 27 degrees for maintenance, but for renewals, it's now 30 degrees. When engineers talk about a rail's stress condition, they usually do it by stating the SFT. So in the rest of this video, when I'm talking about a rail's level of stress, I'm really talking about its SFT. Before we move on, it's worth noting that putting the rail in tension does bring another risk as well. That's broken rails. In cold weather, the rail temperature can drop well below the SFT, which increases the level of tension. And if there's an existing weakness, a defect in the rail, or a problem at a weld, that extra tension makes a break more likely. That's why rails aren't stressed to the highest number possible. Before we move on, a quick word from today's sponsor, Pandrol. This video is about one thing: knowing the stress-free temperature of continuously welded rail, because that number underpins the decisions engineers make when the weather gets hot. Pandrol supports infrastructure managers and maintainers with stress management with tools built for this exact problem. Their VERS equipment is used to determine SFT on site, providing a way to validate the SFT value without cutting into the rail. And anytime the rail needs to move freely during stressing or de-stressing work, that's where Pandrol's Vortox stressing rollers come in. They help the rail move cleanly when it needs to. I've put links to both in the description. Now with that in mind, let's look at what happens when a rail is installed and stressed, and why the SFT doesn't stay fixed forever. When a new rail is installed, for example, to replace a defective section of rail, one end will be welded first. Then the amount of extension required to reach the target SFT is calculated, and the correct gap is cut at the other end of the rail. The rail is then stretched, with rollers used to help the rail move, and it's welded. If it's all been done correctly, that length of rail is now set to the target SFT. But SFT isn't a constant value, as much as track engineers would like it to be. Over time, it can change, and that can reduce your buffer before the rail moves into compression. So what causes that slow leak in SFT, that gradual shift away from its original set value? First is the expansion and contraction cycle that the rail goes through over time, the daily temperature swings, and the bigger seasonal changes across the year. Over time, because the fastening system and the support underneath allow tiny movements, that temperature cycle contributes to small longitudinal movements of the rail, what engineers call creep, and the SFT can slowly shift away from the original value. Second is the passage of trains. Every train puts longitudinal and lateral forces into the rail, and over time, these forces can create tiny movements. Longitudinal forces come mainly from traction and braking, and they are amplified on gradients where trains are working harder or trying to control speeds coming downhill. Then you've got curves, which introduce lateral forces pushing the rail sideways. And on top of that, there's the constant dynamic loading and vibration as wheels pass, which can disturb the rail in small ways over time. Third, the track itself. Its design, its condition, and the work that gets done to it. Perhaps most obviously, any work that cuts the rail, or even just unclips it and frees it from its fastenings, can change the rail's stress condition and then its SFT. Any work to change the alignment of the track can move the rail longitudinally or laterally, which can change the SFT locally. Then there's the condition of the track itself. The fastenings used to hold the rail, along with the pads underneath the rail, are the components primarily charged with keeping it in position and preventing the creep I mentioned earlier. If these are in poor condition and the clips aren't providing the right clamping force, known as toe load, creep is much more likely. And if the support is poor, sleepers not properly supporting, ballast not giving a firm bed, the rail can move under load. It's a small movement, but repeated thousands of times, and that's how the SFT drifts. Each one on its own seems minor, just tiny opportunities for the rail's stress condition to drift. But like a water leak, it can go unnoticed for a long time, and then suddenly matter a lot. Rail stress management isn't just about temperature. It depends on the components that restrain the rail. If you want a quick way to identify the key track components you'll hear mentioned in this video, I've got a track component ID guide linked in both the description and the top right hand corner. It's free to download, so grab your copy now. Imagine the stress-free temperature of a section of track that's been slowly drifting since it was installed and is now 5 degrees Celsius lower. So what? Why does it matter? To see why that matters, you need to understand what maintainers and operators actually use SFT for. SFT is one of the key factors, alongside ballast condition, track construction, and track alignment, which determine what hot weather mitigations need to be applied and when. Those mitigations might include extra monitoring and patrols, or speed restrictions, all aimed at reducing the risk of a buckle, and ultimately a derailment. Because the rail is the source of the compressive forces that drive a buckle, it's fair to say that the SFT is one of the most important inputs into those mitigation decisions. So if the SFT has changed without anyone knowing, you can end up applying mitigations at the wrong time or at the wrong temperature thresholds, which then increases the risk of a buckle. The bottom line is this: for safety and performance, the railway needs to know the correct SFT of its rails. But there's a catch. A rail's SFT can't be seen in a visual inspection. The track can look perfect. It can even be brand new, but you still can't tell what the SFT is just by looking at it. This is where VERS testing comes in. VERS stands for Vertical Rail Stiffness Equipment. VERS testing is a way to determine the stress-free temperature of continuously welded rail. How does it do this? By measuring how much force it takes to lift the rail. Think of a length of rope. The tighter it is, the harder it is to push it down or lift it up. It's harder to deflect. A rail behaves in a similar way. So how is this done in practice? A length of rail, normally around 30 to 35 meters, is unclipped from the sleepers to allow it to move. That unclipped length is then raised onto two support points at either end, creating a bridged length that's clear of the sleepers. The VERS unit is then placed in the center and used to lift the rail while measuring the force and the displacement. In the same way as the rope example, if the rail is in a higher tension, you need more force to get a small lift. If it's in low tension, you get more lift for less force. From the force and displacement values recorded during the lift, you can determine the rail's tension. And if you know the rail temperature at the time, you can then determine the SFT. There are a few other inputs that affect the calculation as well. First, the rail itself, the rail section, and anything that affects its stiffness. Different sections or profiles have different stiffnesses because of their shape and thickness. Wear matters too, because it changes the rail's profile over time. Then there are the material properties of the steel, which are usually fairly consistent because most rails are made to common standards. The second set of inputs is the test setup, the distances between the support points, the first clips, and the verse unit. That defines the beam geometry for doing the calculations. Lastly, on a curve, there's another factor. When the rail is unclipped, if it's in tension, it will tend to straighten slightly and move towards the centre of the curve. To account for this, a versine is measured before and after unclipping, and, once again, when the rail is on its supports. That way, the calculation reflects the rail's actual position during the test. Unclipping, supporting the rail, measuring versines, lifting the rail, taking measurements, and then putting it all back together again. So why is it worth it? We've already covered why it matters to know SFT accurately. To see the benefit of verse testing, let's look at the alternative. The main alternative is to restress the rail. That means cutting the rail, stressing it, and welding it back up. And that brings both cost and risk. You need a welding team, staff to bring the heavy stressing equipment to site and set it up, and competent staff to carry out the stressing calculations. That's a lot of people and kit, and anytime you're welding, there is a chance it doesn't go to plan. Runouts and other issues can mean a failed weld, overruns, or having to come back and redo the work. If you're already cutting into the rail, for example to remove a defect, then restressing at the same time is good maintenance management. But if you're not, you've introduced both cost and risk you might not need it to. Burst testing gives you a non-destructive way to determine whether those works are actually required. It does come with a cost, especially the equipment up front, but over time this investment can save money by reducing unnecessary maintenance works. It lets you target resources, like welders, where they're really needed. Ultimately, it gives engineers the information they need to set hot weather mitigations and plan corrective work accordingly. Summer. The hot weather period is a time of risk for any railway. In the run-up to summer, networks assess readiness and carry out work to put the railway in the best possible condition. A key part of that is knowing which sections of track are at high risk. Mitigations like speed restrictions at these risk sites disrupt the running of trains across the network, delaying services and the passengers on them. But that disruption is still better than dealing with a buckle. With an accurate register of risk sites and clear temperature thresholds for when mitigations kick in, operations teams can plan ahead, add a decent weather forecast, and they can manage that disruption rather than react to it. But all of that relies on having the right information about the track, and the SFT of continuously welded rail is a fundamental part of it. Accurate SFTs mean risks are understood, mitigations are applied at the right thresholds, and the chances of buckles and breaks are reduced. And verse testing is one of the ways to make sure those SFT values are correct. Thanks for watching. I hope you found this useful. If you did, please hit that like button and also subscribe.